Convolutional neural networks. Description. Convolutional neural networks (CNNs) are a class of deep learning models specifically designed for processing structured grid data, such as images. They are particularly effective for tasks involving spatial hierarchies and patterns. Key components. Convolutional layers. Description. Apply convolution operations to the input data, using filters kernels to detect local patterns and features. Features. Filters kernels. Small matrices that slide over the input to produce feature maps. Stride. Step size by which the filter moves across the input. Padding. Adding extra pixels around the input to control the spatial size of the output. Activation functions. Description. Apply a nonlinear transformation to the output of each convolutional layer, introducing nonlinearity into the model. Common functions. ReLU rectified linear unit replaces negative values with 0. Sigmoid squashes output to a range between 0 and 1. Tanh squashes output to a range between -1 and 1. Pooling layers. Description. Reduce the spatial dimensions of the feature maps, retaining the most important information while reducing computational load. Types. Max pooling takes the maximum value from a patch of the feature map. Average pooling takes the average value from a patch of the feature map. Fully connected layers. Description. Connect every neuron in one layer to every neuron in the next layer. Typically used towards the end of the network for classification. Purpose. Aggregate features learned by convolutional and pooling layers to make final predictions. Dropout layers. Description. Randomly set a fraction of input units to 0 during training to prevent overfitting and improve. Generalization. Rate. Fraction of the input units to drop. Training process. Data preparation. Description. Preprocess input data by normalizing, augmenting, and resizing images to fit the model's input requirements. Forward propagation. Description. Pass the input data through the network, layer by layer, to obtain predictions. Loss calculation. Description. Compute the difference between the predicted output and the true labels using a loss function. Backward propagation. Description. Compute gradients of the loss with respect to the model's parameters and update the parameters using an optimization algorithm. Iterative training. Description. Repeat forward and backward propagation for multiple epochs until the model converges or achieves satisfactory performance. Applications. Image classification. Description. Categorize images into predefined classes, such as identifying objects in photos. Object detection. Description. Detect and localize objects within an image, drawing bounding boxes around them. Image segmentation. Description. Partition an image into segments, classifying each pixel to identify regions or objects. Facial recognition. Description. Identify or verify individuals based on their facial features. Medical image analysis. Description. Assist in diagnosing diseases by analyzing medical images such as X-rays, MRIs, and CT scans. Advantages. Automatic feature extraction. Description. Automatically learn hierarchical features from raw data without manual feature engineering. Spatial hierarchies. Description. Capture spatial hierarchies and patterns in data, making them effective for image-related tasks. Parameter sharing. Description. Share parameters across the network, reducing the number of parameters and computational cost. Challenges. Computationally intensive. Description. Require significant computational resources, especially for large-scale models and datasets. Data intensive. Description. Need large amounts of labeled data for effective training. Susceptible to overfitting. Description. Can overfit to training data, requiring techniques like dropout and data augmentation to mitigate. Recent advances. Residual networks ResNets. Description. Use skip connections to allow gradients to flow more easily, addressing the vanishing gradient problem in deep networks. Convolutional neural networks for sequence modeling. Description. Apply CNNs to tasks like natural language processing and time series analysis, expanding their applicability beyond images. Efficient net. Description. Scale model dimensions, depth, width, resolution systematically for improved performance with fewer parameters.